Okay, so the peak is in the center, so the time to peak we're going to say is t sub p. The time all the way to the very end is simply 2 times that t sub p. Okay, how would we find this time to peak? Well, in the y dimension, what do we know? We know that the velocity, think of the equation that says the velocity is the initial velocity plus at. Now let's take this equation and let's apply it to the y dimension. We have the velocity in the y component is equal to the initial velocity in the y component, okay, plus at. In this case, a, again, is minus g. So we would have the velocity in the y component equals the initial velocity in the y component minus gt. Okay, now just as before, we're going to look at the situation where t is equal to tp. Now we put a t sub p because we're going to evaluate that, and we know that the y velocity is exactly 0 at the peak. Okay? Since y is exactly 0, we can say 0 equals the initial velocity. Now the initial velocity in the y dimension is VO times the sine of the angle minus g times t sub p. We can go ahead and solve for t sub p now. This is t sub p. We solve for t sub p and we get g, add this to both sides, g t sub p equals the initial velocity times the sine of the angle. We can solve for t sub p. Time to peak is the initial velocity times the sine of the angle divided by g. Okay, so it turns out we can solve for the time to the peak quite easily. So that means if that's time to peak, then twice that is simply 2 times time to peak, is simply 2 times the velocity, the initial velocity times sine of theta divided by g. Okay, once we have the total time, the total distance from here to here, or what we call the range, delta x, delta x max, or the range, or what I sometimes call, is x sub range, is equal to, again, it's the initial velocity in the x dimension times the total time. The total time is simply t2 times t sub p. Okay? So again, the range is the velocity in the horizontal dimension, which is v sub ox, times the total time from here to here, which is 2 t sub p, 2 times tp. So the initial velocity in the x dimension is v sub o times cosine of the angle in the x dimension times the total time, which is this. So I'm going to take this and I'm going to substitute it in here. So I'm going to take this and I'm going to just stick it right in here, and I get 2 VO sine of theta all divided by g. Okay? So now I have this expression, and can I do anything with this expression? I sure can. This is multiplied together. Notice I have a VO and a VO. Notice I have a 2, so I can say 2 VO squared times cosine of the angle times sine of the angle, cosine of the angle times the sine of the angle, all divided by g. Okay, this is the x range. This is a distance. This is a nice formula for the range. Turns out, can we simplify this a little bit more? Yes, we can. And if you look in this, there's a trig identity that if you've had trig before, you may know, but if you don't, you'll just have to take my word for it, I suppose. But there's a trig identity that goes like this. That the cosine of an angle, let me write it over here. The cosine of an angle times the sine of the angle equals sine of 2 theta over 2. Sine of 2 theta over 2. Now this is a trig. If you look in your trig tables, trig identity tables, you will see this sine of theta, sine of an angle times cosine of the angle times sine of the angle is equal to sine of 2 times theta divided by 2. Okay. Now let me show you an example of this. Because some students get confused when they have a theta and then suddenly have 2 theta. Just for right now, I'm going to erase this briefly. And again, this is a trigonometric identity. Okay, let's do an example. Suppose, let's just pick an angle. Suppose the angle is 25 degrees. In fact, it will work for any angle. I just arbitrarily pick 25 degrees. What we're saying is this, is that the cosine of 25 degrees times the sine of 25 degrees should equal, and here I'm going to put a question mark because maybe you don't believe it, should equal the sine of 2 times 25 degrees. Notice it's 2 times the angle, so it's 2 times 25 degrees, all divided by 2. Well, this is the same thing on the right-hand side of sine 2 times 25 is 50 degrees, all divided by 2. Okay, take out your calculator. I have mine. Make sure you're in degrees, not radians. Take 25 cosine, multiply that to 25 sine, and what do we get? I get, on my calculator, 0.38302. Okay? Now, that's the left-hand side. Let's take the right-hand side. Take 50 degrees, take the sine of that, divide it by 2, and I get 0.38302. I get the exact same number. So, now that's not a proof. It's really just a demonstration that it works at one particular angle. An actual proof would be where you prove it to be true for all angles. We haven't done that because this isn't a geometry class or a trig class, but this is just to show you a little bit of that this trig identity really works, and to show you that when we say the sine of 2 theta, you put in theta and you multiply it by 2. That's actually what we mean, sine of 2 theta. Okay? Well, a little bit of discussion on that trig identity, but we're going to use that trig identity. Notice that we have Here we have sine of theta and cosine of theta. Notice we have cosine theta, sine of theta. In the trig identity is cosine theta times sine of theta. So this means I can take this and I can replace this. Well, I'll write it up here. The x range is equal to 2 VO squared, and in place of cosine and sine, I'm going to put this over here, sine of 2 theta, all divided by 2. I'm just going to simply kind of write it like that, all divided by g. I'm going to erase this so you don't get confused here. I'm going to erase this. Notice I can cancel out these 2's, and what I'm left with is that the range is equal to VO squared times sine of 2 theta, all divided by g. This is a range equation, and you'll find that range equation on page 118 in your textbook. Okay? It would be good for you to actually know how to use this equation. Well, you have to know how to use it. For the test, you're actually going to have to memorize this equation, or if you don't memorize it, you're going to have to use it, and so you're going to have to know how to derive it. So you should know how to derive it anyway, but it would be good for you to memorize it nonetheless. Okay. So again, just to reiterate here, how would you use this? Suppose you had an initial velocity of, let's say, 100 feet per second. I'm switching to English units here, and I was shooting, say, an arrow at 100 feet per second at an angle of 40 degrees. If I wanted to see where that arrow would land, I'm on a flat field. This range from this x range from here, I would plug in the initial velocity, square it, times take sine of 2 times 40 degrees and divide it by g, which in the English would be 32 feet per second squared. Okay? So we're not going to plug in any numbers to that right now. We're just going to move on to a few other examples and kind of learn how to solve just a few other types of two-dimensional problems. If you now turn to page 122, example 4.5, it's a cannon on top of a cliff and it's shooting off. So for example, here's the ground, you have a cliff here, and you have a cannon that's shooting, say, a ball, it's horizontal, and it's shooting it off at a certain velocity. And the question is, where will this land? Right here. So what we want to solve is this distance, delta x, from the cliff. Okay. What you know is that it's the initial velocity of the cannon. Say you know what the initial velocity is. You know that it's horizontal. And, whoops, you know what this distance is. What are these? We'll call this height, the height from here to here. The height, we'll call this the height, or we'll call that, well, we'll just leave it as height. The height from here to here, we'll call it h. You know what that is, and you want to know what this is. Well, how do we solve this kind of problem? Well, this is kind of like the range equation, but notice it's only really 1/2 of the range. So, and we can't use the range equation because the range equation assumes that you're starting initially at a certain angle to the horizontal. Here we're not. Here we're starting vertical. We're starting purely horizontal. So we can't use the range equation here. So we're going to have to just solve this directly. So we're going to have to, first of all, we're going to have to solve for the time. Now notice that we don't know, well, what do we know? One thing that can aid us, we know that what is the initial velocity? The initial velocity in the y is what? Is 0. There is no initial velocity. The initial velocity in the y is 0. There's no initial velocity here. So in fact, we can use that. We can use that very nicely to our advantage to solve for the time. Think of this equation. The equation that says x equals the initial velocity times time plus 1/2 at squared. We're going to take this equation and look at it in the y dimension. Okay, in the y dimension. So if you take this equation, look at it in the y dimension, what we have is that the y displacement is equal to the initial velocity in the y component times time plus 1/2 at squared, where a is now equal to minus g, is the acceleration of gravity going down. Okay? If we solve for the total time it takes to get from here down to the bottom, we know that the initial velocity here is 0. So this entire first term drops out. And so this h now becomes h. Okay? I'm going to say this becomes h. So we have h now, which is this vertical distance, equals, there's a minus 1/2 gt squared. Okay? Now, notice there is a minus sign here. What about this h? Remember our datum here, if we set y equal 0, y equals 0 right here where it starts, that means when we come down, as this saying, whoops, as this comes down, that this distance is really a negative h. Okay? It's going to be a negative number. Up is positive, down is negative. So when we have an h here, the h is really a negative number. We're going to say negative h. So therefore, I can come in here and say there's a negative sign in front of h because it's down below our initial datum. Notice that the two negative signs cancel out. I'm going to solve for t now, so I take 2h equals gt squared divided by g. 2h divided by g equals t squared, or 2h divided by g square root of, that's equal to t. Okay? So my t, the total time from here all the way down to here, or how long it takes to fall, is the square root of 2 times h divided by g. Now that I have this, I can work on the horizontal component. I'm going to erase this now. Okay. In the horizontal component, or the x dimension, the total distance traveled is equal to the initial velocity, which is purely in the x dimension, times t. Right? In other words, the horizontal velocity is always the same. Therefore, this horizontal distance traveled is simply the velocity times the time. So the initial velocity times, here's t, I'm going to plug that in, the square root of 2 times h divided by g. Okay, so this would be an expression of the range. Well, not the range. We can't call it the range, but this distance from the cliff to where it hits the ground. It would be the initial velocity times the square root of 2h all divided by g. Okay. Suppose I'm going to add one more thing here. This is not in the book. At least I don't think it is. No, it's not. I'm going to add one more thing into here. No extra charge for this extra thing I'm going to add in. Okay, notice that that all this is true. That's this. But suppose we want to take, suppose the problem said, this is a little bit harder problem I'm going to give you here. Suppose we wanted to say, when this lands, what is this final velocity? Okay? Notice that the final velocity has two components. It has a component in the x dimension, and it has a component, it's not a, I shouldn't say, I'm going to write f means final. It has a final component in the x dimension, and it has a final component in the y dimension. Okay, whereas that, I'll do it this way. So really, this vector, when this velocity, when the cannonball hits the ground, its velocity component can be broken up into two parts. The horizontal component and the y component. Okay? Can we solve for that? Absolutely we can. How do we do it? Well, the horizontal component is quite easy. We know what that is. It's simply VO. In the x direction, it hasn't changed. Okay, so this final velocity in the x dimension is simply the initial velocity here. It hasn't changed. But the y is a different story. We know that the initial velocity in the y is 0. There is no initial velocity in the y. But the final y velocity, how do we solve for that? Well, we can solve it for this way. Think of the equation v squared equals VO squared plus 2a delta x. Let's look at this in the y dimension. Okay, here's the y component, the y velocity, the initial y velocity, and I'm going to put minus g. And instead of delta x, it's delta y, which is h. Okay, so this would be this equation, but in the y dimension. Okay, the initial velocity is 0, right? Initial velocity is 0. Notice we have a minus 2g, and notice there's a minus number here, but notice that the h really has to have a minus h in it because we're going in the negative direction. Notice that the minuses cancel out, and so that the final velocity squared equals 2gh. The final velocity in the y is the square root of 2gh. Okay, so that comes up here. So we know that we have just solved for what the final velocity in the y component is the square root of 2gh all in the y dimension. Okay? So, if we really wanted to, now this is not even a homework problem. We're just doing some physics here for fun. So the final velocity is really this. Now if we wanted to say what's the magnitude of the final y velocity, we could calculate that. How do we calculate it? We would take this quantity, square it, add it to this quantity, square it, in the square root of that. So as an example, the magnitude of this would be VO squared plus, we square this, we get 2GH, and you take the square root. That will be the magnitude of the final velocity. Could we calculate what this angle was? Yes, we could. We could do it by taking the tangent function. Okay, that is this angle here, that it hits the ground. Could we calculate that? Yes, we could, because we know that the tangent is the y component divided by the x component, which is, here's the y component, and here's the x component. And by taking the inverse tangent, we could calculate what that angle was. Okay, we do not have any homework problems like this, but I just wanted to show you that problems like this can easily be solved. Okay, there's one more thing I think we want to cover, and that's on page 125, another example of a problem. Look on page 125, example 4.6. And here what we have a little bit different situation here. What you have is someone shooting an arrow, purely horizontal, and the arrow is purely horizontal, and the arrow drops because of gravity, and you hit a tree, and what you want to know is, or maybe this is maybe arrows a bit, maybe this is like a BB gun, and you shoot it purely horizontal, and you sight here, but the BB hits somewhere here. So this distance h. That is, maybe you have sights, and where the bullseye you see is right here, but where the actual BB hits is a little bit lower. And why is it lower? It's lower because gravity is pulling the BB down as it flies, and it actually hits here, even though you shot perfectly horizontal. This is why when you shoot, you have to aim a little bit high to overcome gravity. Okay, but and we could solve that situation too, but for right now, let's assume that we're shooting purely horizontal. The angle here is 0. There's no horizontal, no horizontal angle above the x-axis or below. It's purely horizontal. And let's say, well, that we know this distance. We know what x is. We know what let's say we know what our initial velocity is, and we want to solve for how much drop we're going to have. Say this is 100 meters. That's a long way, almost 300 feet, around 300 feet, and we're shooting maybe like a, well, really long arrow or something like that. We don't know how much drop we're going to have. Okay. How do we solve this problem? It's similar in a way to the other problem that we just solved. In fact, it's actually quite similar. One of the things what we can do again is look at the equation, and we're going to look at this in the y dimension. We're going to say the equation x equal VOT plus 1/2 AT squared. In the vertical dimension, in the y dimension, this will be y equals the initial velocity in the y component times t minus 1/2 g, acceleration g, times t squared. Notice that the initial velocity here in the y component is 0. So this becomes 0. And what we're left with is that at a certain time, the time of travel, whatever time of travel it is from here to here, or to say t equals the time elapsed during flight. That's what t is. And so this y here is going to be, here's our datum, y equals 0. So this distance here from here to here is minus h. Okay, we have plus y in this direction, we have minus y in this direction. So this is minus h down. So this becomes minus h. So we have minus h equals minus 1/2 gt squared. Minuses cancel out, and again we can solve for t, which is just like the other time. So we have 2g over, 2h over g equals t squared, or t equals the square root of 2h over over g. Okay. So we can solve for the time, and that's what the time is, the time of travel. Well, now how will that help us? Well, that will help us because